Okay, Physics 11H, I realize I did not assign the Regents questions, which I should have, but I'm just going to do some of them now for you and then post the solutions to this as soon as I get them written up so you can check them out. All right, so there's actually two sheets here. It's worksheet 3.1.1 and 3.1.2. The first one's momentum and impulse. The second one are conservation of momentum. And let me tell you, if you do these and go through the solutions and watch these videos, you're going to be in really good shape for momentum and impulse. So I'm going to kind of go through this. I'm going to write some of them up here. I'm going to do some notes on the side. I know you probably can't see this too well here, so I'll try to do some of the scrap work over here, but I'm going to try to do this kind of quickly. All right, so determine the momentum of a 20 kilogram object that's moving at 4 meters per second. All right, P equals mv. I just wrote ma out of habit. P equals mv. So P is momentum, mass, velocity. So it's literally just 20 kilograms times 4 meters per second. That gives us 80. And the units are just kilograms times meters per second. Bam, we got it right. Don't even need to bust out my calculator for that one. All right. Number 2, determine the speed of a 25 kilogram object that has a momentum of 100 kilograms times meter per second. All right, P equals mv. Therefore, V would be P over m. So it's got a momentum of 100 kilograms times meters per second divided by 25 kilograms. That gives us a velocity of 4 meters per second. Awesome. Number 3, 10 Newton force acts on a 4 kilogram object that's initially at rest for 0.5 seconds. Calculate the impulse imparted to the object by this force. All right, J, impulse, is force times time. It is also equal to the change in momentum, which is, they don't tell you this on the reference table, it's m delta v. All right, change in momentum is m delta v. But anyhow, since we have the force, we have the mass, and we have the time, we can just use force times time for impulse. So J equals 10 newtons times the time of 0.5 seconds. So the impulse is 10 times 0.5, which is 5.0 newton seconds. A newton second is the same as a kilogram meter per second. It's pretty easy to prove that. Calculate the object's final speed. Well, this is where we do the m delta v, okay? So you know the impulse is 5 newton seconds. All right? And the amount of impulse you give something is equal to its change in momentum. So I know that 5.0 newton seconds has to be equal to m delta v, or change in momentum. This equation is not on the reference table, m delta v. You need to know that one. All right, so divide both sides by the mass. I'm going to get the change in velocity. So delta v equals 5.0 newton seconds divided by the mass, which is 4 kilograms. 5 over 4 is 1.25 meters per second. That's the change in velocity. But since it starts at rest, right, delta v equals v final minus v initial. This term is just 0 because it started at rest. V initial is 0, so v final must just equal 1.25 meters per second. But you should probably just state that. All right. Here we go. Number 4, 1.5 times 10 to the third kilogram car is moving at 10 meters per second east. A braking force acts on the car for 5 seconds, reducing its velocity to 2 meters per second east. All right, determine the impulse experienced by the car. All right, we've got mass, we've got V, we've got T, the initial, V final, impulse. Now, I'm not given the force, right? So, J equals force times time isn't going to work. But that also has to be equal to the change in momentum. So that has to be equal to m delta v. So therefore, I can say impulse equals m delta v as well. So remember, for momentum and change in momentum and impulse are the same thing. You can calculate it either way. So impulse equals m delta v. Let me plug in. Mass 1.5 times 10 to the third kilograms. This is a heavy vehicle. Hand is already cramping up. Change in velocity. So I'm going from 10 meters per second down to 2 meters per second. So that's negative 8 meters per second is our change in velocity. So I multiply this out, 1.5. You should not write it as E4. You should never actually write it like that, although that's how we plug it into our calculator. E3 times negative 8 gives us about negative 12,000, and the units, you just multiply the units, kilograms times meters per second. Great, determine the magnitude and direction of the braking force. So now we know the impulse is negative 12,000. J equals force times time. So the force is going to be equal to the impulse over the time. All right, so the force must be the impulse, negative 12,000. And I got a negative change in velocity because of my signs here. This is positive, this is positive. So my change in velocity is negative. So negative 12,000 newtons divided by the time of how many seconds? 5.0 seconds. All right. Oops. Newton seconds. This unit on top. I was going to say, geez, this isn't going to cancel out right. 12,000. I didn't need to retype that. Divided by 5 is 2,400. So the force is negative 2,400 newtons. But on the Regents, it might say, you know, magnitude and direction. Well, that's a valid direction, negative 2,400, based on the way we drew this. However, you should probably say it like that. You know, we've got north, south, west, and east. West is, you know, towards California. The left coast, as they call it. So 2,400 newtons west, which we have there. All right, vector quantity, magnitude, and direction. Number 5, a 60 kilogram person jumps off a platform, landing while moving 2.0 meters per second. Determine the force exerted on the person's feet when he lands. He stops in 0.25 seconds. So right before he hits the ground, right? Jump down off of something. He's traveling at 2.0 meters per second. He comes to a stop. Right? V final equals 0. The initial. Alright? Comes to a stop in a time of 0.25 seconds. Its mass is 60 kilograms. Determine the force exerted. So, this we go right to force times time equals m delta v. And this is actually where we started this unit, just equating those two things. Force times time equals m delta v. So really this is Newton's second law. We're going to divide both sides by time, m delta v over t. All right, so we've got 60 kilograms. Change in velocity. Well, this is kind of an interesting thing. It was moving down initially, so maybe I should make that negative, right? The initial velocity. So change in velocity, final minus initial, 0 minus negative 2 meters per second. It asks the force. Geez, it doesn't say magnitude of the force. It probably should say magnitude, and then you wouldn't have to worry about the sign. You know the velocity is changing by 2 meters per second. The time it takes is 0.25 seconds. So 60 times 2 divided by 0.25 gives me 480. Yes, I know that the solution's written right there, but you know, I just like to check my work. All right, so one side of this done. Let's see, should we move on to the other side? All right, this is already getting kind of long, but oh well, it's there. I'm making the solutions anyways. I'll post it. 1,500 kilogram railroad car is moving with a velocity of 4 meters per second in a direction that is 20 degrees north of east. Okay. In the diagram below, starting from point P, draw a vector that represents a railroad car's momentum using a scale of 1 centimeter equals 2 times 10 to the third kilograms meters per second. Oh boy. Okay. So first let's figure out what the momentum is. That was unexpected. That was an unexpected question. I didn't read them before I started doing this. But it's a good one. Drawing vectors, you know? All right, that's going to be 6,000 newtons, the momentum. And they want 1 centimeter equals 2 times 10 to the third kilograms. So that's 2,000 kilograms times meter per second. So momentum is a vector quantity. So I just happen to have, this is kind of funny, I happen to have a protractor literally right by my setup if I can grab it. All right. So, okay, let's go for it. 20 degrees. I wasn't expecting to have to bust that out. 20 degrees. I go over here. There's 20 degrees there. I got to put a little dot there. It's off the paper. Oh well. And then it's got to be 3 centimeters long, I think. I'm going to go right into what I just did here. So I line my protractor up here now. 1, 2, 3. Put a little dot there. I draw the line. All right. And then you got to make sure that the arrowhead doesn't extend past that. 20 degrees. That was unexpected. So if it's 2,000, it's kilograms times second. If it's 2,000 kilograms times second per 1 centimeter, we need a 3 centimeter long line in order to represent that vector. Unexpected. Interesting. What is the magnitude of the net force acting on a 2 times 10 to the third kilogram car as it accelerates from rest to a speed of 15 meters per second in 5 seconds? Listen, this is just use Newton's second law. It's just reinforcing the fact that impulse is just a representation of Newton's second law, ma. All right, so 2 times 10 to the third kilograms, the acceleration here, delta v over t, from rest to a speed of 15 meters per second. Let me write that up here for you, delta v over t. It's gaining 15 meters per second in 5 seconds, so that's going to be 3. So it should be 6 times 10 to the third newtons, right? I'm not even going to bust out the calculator. If I made a mistake, oh well. Fix me, correct me, tell me. All right. The magnitude of the momentum of an object is 64 kilograms meters per second. If the velocity of the object is doubled, the magnitude of the object's momentum is, it's doubled. It's doubled. P equals mv. If you 2x the velocity, that means you 2x the momentum. All right? 64 times 2 is going to be 128. Bam. Force of 20 newtons exerted on a car for 10 seconds. For what period of time must a 50 newton force act on the car to produce the same impulse? All right, so J equals force times time. That would be 20 times 10 seconds, or 200. If I have a 50 newton force, I would only have to act on it for 4 seconds in order to produce a 200 newton second impulse. All right, some of that proportional reasoning, a lot of Regents questions are like that. If they move to do a Regents quiz online, multiple choice probably is what it would be. God knows what the scaling factors would be for that. But these are the kind of questions they would focus on. A bullet traveling at 250 meters per second is brought to rest by an impulse of 5 newton seconds. What is the mass of the bullet? Okay, force times time is m delta v. This is 5.0 newton seconds. Mass is unknown. Change of velocity is going to be negative 250 meters per second. Negative signs don't even matter. I guess that would probably be negative because it's slowing it down, that force. So the mass of the bullet is 5 over 250. Or 0.02. All right, so we got to figure out which one of these that is. So let's write this in scientific notation. 1, 2, 2 times 10 to the negative 2. Bam, it's 4. An object of mass m is moving at a velocity v, is stopped by a force and time t. How much force would we need to stop mass in time t over 4? Okay, so force times time equals m delta v. All right, so if we want to make this 4 times smaller, all right, then we're going to need 4 times bigger force to stop it. Okay, same mass, right? Mass and mass. So force times time needs to be 4 times smaller, but I want to keep the product of this. I'm still stopping the same bullet, moving it, same object, same velocity. So whatever this is, let's say this comes out to be 1, right? Your mass times change in velocity for this object. Well, if I divide t by 4, I then have to multiply the force by 4 so that they cancel and we get a 1. All right, so there's just a quick on that worksheet 3.1.1. I'll make another video on 3.1.2. Maybe I won't do every problem. This got a little bit long. I'll pick some selected ones off the next worksheet. All right, see you later.